welcome back. It's a pleasure to have our next speaker, Matthew Jenssen, who is lecturer at University of Birmingham, and he will talk on the singularity probability of a random symmetric matrix being exponentially small.
Okay, thanks so much, Liana, for organizing this and inviting me. I realized on closer inspection on the mini symposium title this morning that my talk actually doesn't fit at all. In particular, there won't be any graph theory in this talk, but if you allow me to change the word graph theory for combinatorics, then I think I'm no longer an imposter. So hopefully that's okay. And yeah, everything I'm going to talk about today is joint work with Marcelo Campos from IMPA in Rio, Marcus Michelin from UIC in Chicago, and Julian Sahasrabuddhe at Cambridge. Okay, let me start actually by deleting the word symmetric from my title. So we're just talking about random matrices. What do I mean by that? So first, it's nice to consider the following problem, which is we have a uniformly random n by n matrix with entries in plus or minus 1. And an old problem asks, what's the probability that this random matrix is singular as determinant 0? And there's a very old folklore conjecture that says the probability that the determinant of B is 0 should be this funny expression here. What is this expression? This is just the probability that 2 rows or columns are equal. So we have n squared pairs of rows or columns that could potentially be equal. And what's the probability that they are equal? Well, 2 to the minus n plus 1. Either they're all, oh, sorry, I shouldn't say equal, I should say proportional, equal up to sign. Okay, great. So let me mention some highlights on progress towards this lovely conjecture. It's actually not even obvious that this probability should go to 0 with n. And this was first shown back in 1967 by Komlosh, who showed that the singularity probability goes to 0 at least as fast as 1 over root n. And then almost 30 years later, a big breakthrough result by Khan, Komlosh, and Semeradi, they showed that it goes to 0 exponentially fast with n. And then some subsequent improvements fighting over the base of the exponent. Remember, what's the correct base we're looking for? It's 1/2. So Tau and Vu got 3/4. Bourgain, Vu, and Wood got 1 over root 2. And finally, in a recent breakthrough of Tikhomarov, getting the correct base of the exponent, 1/2 plus little o1 to the n. So this folklore conjecture is still open if you really want the first order asymptotic n squared in front there. But at least the base of the exponent is resolved. And I should mention here a recent breakthrough of Jane, Sa, and Sawney, which says actually this folklore conjecture is true if the entries of B are non-uniform. So I'm not 1/2, 1/2, and minus 1, 1, but as soon as I'm non-uniform, then this conjecture is true. What do I mean by this conjecture is true? You should, of course, replace this by the probability that 2 rows or 2 columns are equal. Okay, great. So now let me introduce the word symmetric into my problem. So I'm just going to ask the exact same question, except now I'm going to impose the condition that my random matrix is symmetric. And by a symmetric plus minus 1 matrix. I suppose now that the matrix is symmetric of a graph, so maybe maybe this is some graph theory in this talk after all. Although that wouldn't be useful, this perspective, but there we go. So yeah, remember, again, we're looking for something exponential. And here we have an e to the minus root 10. And then 2 recent small improvements to this bound by Jane, Sa, and Sawney, and then by myself, Marcus, Marcelo, and Julian again, getting e to the minus root n log n. And so you see there's a sort of convergence of results here to this e to the minus root n log n. It turns out this is not a coincidence. There's actually a very good reason. There's a very natural barrier at root n log n, which I'll discuss a bit later in the talk. Okay, but the result I want to talk about today is an exponential bound of the singularity probability. So again, just let A be a uniformly random symmetric plus minus one matrix. And the probability that A is singular is exponentially small in n. So e to the minus constant n, where c is some small constant, small absolute constant. Okay, so in the rest of the talk, I'm going to sketch a proof of this result. And let me start by, if you've never thought about this kind of thing before, just a general approach to this problem, general approach to the singularity. So let me start with a trivial observation that saying the determinant of a matrix is 0 is equivalent to saying that there exists a vector on the unit sphere that's in the kernel that gets mapped to 0 by A. So then I can write that the probability that the determinant is 0 is the union of these events. And now I want to do a union bound. But of course, there's a bit of a problem here that the unit sphere is rather large. So there are a couple of approaches to get around this. One common approach is to actually not work over the reals, work over some finite field like zp to the n or something. But the approach that we'll take is also a common approach, is to discretize our world, to discretize the unit sphere. And so the discretization I'm going to work with is, I'm actually going to take the whole closed ball, say, centered at 0, radius 1, intersect some fine lattice, epsilon over root n, z to the n. So here's my fancy picture in 2 dimensions of us discretizing the 2-dimensional ball. So now I'm going to try and replace the unit sphere here with my discrete ball. And now, once I've done that, it will at least make sense, right? This is a finite set. It will at least make sense to try and do a union bound. Okay, so that's the first vague step. Okay, so the first sort of serious step that I want to take in this proof is actually a rather strange looking step at first. But it's to replace A, remember that's our plus minus one symmetric matrix, with a more confusing but much more well-behaved matrix, M. So what is M? M, I'm just going to zero out the top left D by D submatrix of A and the bottom right n minus D by n minus D. And here think of D as like n over 100 or something, some constant times n. And now H is no longer going to be, well, it's no longer going to be plus minus 1 with probability 1/2 on each, but I'm going to make these coin flips a bit lazy. So it's going to be 0 with probability 3/4, and it's going to be plus or minus 1. Each entry will be plus or minus 1 with probability 1/8. So just remember, before we had everything was plus minus 1, probability 1/2, 1/2. Now I've just laserfied these coin tosses, if you like. And the reason for doing this actually goes back to the breakthrough work of Kahn, Komlosh, and Zemerady. They did a very similar move. And one reason is it makes certain Fourier arguments much more well-behaved. In particular, the Fourier transform of events mv equals 0 is positive. But we won't get into that in this talk. But another reason is zeroing out these things kind of gets rid of some nasty dependencies, which we'll see a little later. So there are a couple of good reasons for making this move. Okay, and now I'm going to try and do this move where I discretize the sphere. But first, I'm going to split up my sphere by picking a scale for each vector v. So this is a slightly confusing condition, which could largely be ignored. So I'm going to take a vector v and say it has scale epsilon if the probability that it goes close to 0 under M is roughly epsilon to the n, essentially. And so this should be thought of as like the right scale under a discretization to think of V in this problem. This is sort of the point at which anti-concentration properties of V start to be felt. So this MV, its most popular point is going to be 0. Most wants to be at 0. So saying that this is like L epsilon to the n, upper bounding that probability is some anti-concentration statement. So this is just sort of the right scale to look at V for this problem. So different V, we're going to be discretizing at different scales for different V. And so our kind of discretization move is to say, aha, well, you can show that the probability that AV equals 0 for some V at that scale is upper bounded by the probability that MV is close to 0 for some V in my discrete sphere. So two things have happened here. One is that I've replaced A with M. And it shouldn't be too surprising that I can do this, because if you look at M, it wants to be more 0 than A does. It wants to map things to 0 more than A does. So it shouldn't be too surprising that we can replace A with M and get upper bound like this. And the other thing that's happened is we've replaced equals 0 here to close to 0. And that's just because if I have a V on my unit sphere, it gets mapped to 0 by A. If I push it onto my net, maybe M doesn't map it to 0, but it just maps it close to 0. So this is some cost for discretizing. If I push a vector V into my net, I might perturb the image slightly. Okay, but the win is we've replaced something continuous with something discrete. So now let's...
Is AV equal to 0?
Yes.
V at scale epsilon, what does it mean?
Sorry. When I say V at scale epsilon, this is the definition of the scale of V. So I say V has scale epsilon if this condition is satisfied. That the probability it gets mapped close to 0 is roughly epsilon to the n. So for every vector V, I associate some scale epsilon. So this is AV equals 0 for some V with scale epsilon. Does that make sense? So I've just chopped up my sphere at different scales, epsilon. And this is saying, what's the probability that V is in the kernel where V is in this slice of my sphere? Okay. Good. So yeah, we can try and do a union bound again, but the problem is immediately it doesn't work. Why? Well, if we want to do a union bound, let's think about the size of this discrete sphere. It turns out it's essentially 1 over epsilon to the n. But the probability of this event happening, we've just said, by definition, it's L epsilon to the n. So when I multiply this quantity by this quantity, I get something much larger than 1, which isn't a great bound on a probability. The problem is this net is too large. Here you should think of L as some large constant. So the net is too large. So the idea is to refine the net and just remember that, okay, I'm in my discrete sphere, but also V has this special property that it's at scale epsilon, meaning that the probability it's close to 0 is roughly L epsilon to the n. So let me just remember that property of V. And what I'm going to show is almost all vectors in my discrete sphere don't satisfy this property. In fact, I can throw away tons and tons of vectors from lambda epsilon, and this is still a good net for vectors at scale epsilon. The way we'll do that is by taking a probabilistic viewpoint of the discrete sphere lambda epsilon and say, if V is chosen uniformly at random, then the probability that I satisfy this condition is extremely small. So taking this probabilistic viewpoint of the sphere as what it actually goes was one of the big innovations of Tikhomarov in his breakthrough work, and he termed it inversion of randomness. Not only looking at the randomness in the matrix M, but taking a probabilistic viewpoint of the sphere itself. And if we do this, so this, I actually claim this lemma is enough to complete our proof, because now we can do our union bound. So let me show you how it's enough for us. Let's try and do a union bound again. So now I'm not union bounding over the whole discrete sphere, but this now refined net, n epsilon. And I'm summing the probability that M maps V close to 0. Well, this was the size of my original net, but I've just said that the probability that V lands, a random V lands in lambda epsilon is 1 over L squared to the n. So this whole thing here is an upper bound in the size of my new refined net, n epsilon. Okay, now I can bound this probability, the probability that V gets mapped close to 0, by 2L epsilon to the n by definition. And what I get is something exponentially small if I choose L large enough. So, right, that explains at a high level why this lemma is enough. So maybe this is a good point to take any questions. Okay, so if there aren't any questions, yeah,
I have a quick question. So,
yeah.
So why don't confused? Why don't we sum up over epsilon anywhere, or we do?
Oh, we do. Yeah. Sorry. So at the end of the day, I will have to take some sum over epsilon as well. Yeah. So I'll just take some dyadic, thing over epsilon, and yeah, there's an extra union bound there that I swept under the rug. Yeah. Yeah, so that's a really good point. Thanks for that question. Okay. So yeah, a good way to bound this probability, of course, is to look at, let's just look at the first moment of the thing that we're trying to bound. So let me look at the expectation over V of the probability. And now let me, from now on, this is kind of ugly to keep writing. Let me just write MV equals 0. It's a bit easier on the eye and actually is conceptually the same. So I'm just replacing this condition being close to 0 and replacing it with the probability that MV is exactly 0 again, just for simplicity. So let me try and analyze the first moment of this probability. And then by Markov, I'm going to try and get a bound like this. Okay, so before we do that, though, let's take a couple of steps back and just remember what M is and what this event MV equals 0 means. So remember, M is this matrix where I've zeroed out the top left and bottom right, the top left d by d and the bottom right n minus d by n minus d. And I have this lazy matrix H over here. So let me split V up into U and W, U being just the first D coordinates of V and W being the rest. Then I can just write MV as H transpose times W on top of HU. So just something trivial here. And so it turns out that there's a nice way of describing kind of previous approaches to this problem, which they've essentially forgotten half of the matrix. So you can bound the probability that MV equals 0 just by the probability that this lower half is 0. And why would you want to do that? Well, there's a huge advantage that the entries of H are IID, they're independent, which is not true for M. So this is very, very tempting move to do. But it turns out as soon as you do something like this and forget and just use the randomness in one half of the matrix, you're sort of doomed to meet this root n log n bound that I mentioned earlier. And so to break through that barrier, we're going to have to reuse the randomness somehow. of this matrix. So the way we're going to do that is we're going to condition on some pseudo-randomness condition on H and bound the probability that HU is 0 subject to this pseudo-randomness condition. And then up here, we're going to use randomness in W to try and bound the probability that H transpose W is 0, subject to H being pseudo-random. So let me just say that again. We're just going to use the randomness in H down here and the randomness in the vector upstairs. Okay, that's very vague. What do I mean by that? So how do we quantify a pseudo-randomness of H? It's actually very simple. We're going to just look at the singular values of H and just condition on how many singular values are large. So let me just order the singular values of H in decreasing order. So sigma 1 is the largest singular value. Let me say sigma d is the smallest. And I'll let EK be the event that the bottom K singular values are small. Small meaning less than some small constant times root n. So this is just some condition on the singular values of H. And now I can rewrite this probability, the probability that MV equals 0. Well, first, trivially, it's just the probability that both these things are 0, H transpose W and H of U are 0. And now these events, EK, split up my probability space. So let me just partition this probability according to EK. So just condition successively on EK, depending on which EK occurs. And it turns out what's going to happen is there's going to be a nice trade-off between these two probabilities. So K being large is going to make this probability much smaller, or it's going to make this probability much larger. And it turns out that you should think of E naught. What's E naught? That's the probability that what is E naught? It's the probability that no singular value is large, that all the singular values are large. And that's the typical event. And actually what's interesting here is this actually relies on H being a tall matrix. It's D by n minus D, so it's like a tall, thin matrix. This isn't true for square matrices. So it's curious here that it's we're somehow using the fact that properties of this tall submatrix of M. A square matrix typically has smaller singular value, like 1 over root n. Where here I'm claiming typically all singular values of this tall matrix are at least root n. Okay, but we're going to have to control these successively more atypical events, E1, E2, E3, and so on. Okay, and the way we do this is in 2 stages. So first, I claim that we can get a bound on this probability as follows. So it turns out that understanding these 2 events separately is actually fairly straightforward. And you can show that the probability without too much difficulty that HU is 0 is like epsilon to the n minus d. Remember, epsilon is the scale of V, and it's the scale at which we're discretizing our sphere. If you remember the definition of our discrete sphere. And the probability that the singular values of K behave like this, that there are K small ones, is exponentially small, is e to the minus nk. It turns out this is true unless U is highly structured. But it turns out this structure is going to be so rare that we can essentially ignore it in this calculation. But I'll return to that in one slide's time. So I just want you to think about bounding this probability uniformly in the sum by this. And it turns out that this bound is actually the meat of the problem. So I'll spend the next couple of slides just talking about this probability. Okay, but before I do that, let me explain how we deal with these terms. So remember, we were interested in the expectation of this probability. So let me take the expectation over my random vector now throughout this sum. And Okay, and I've uniformly bounded these terms here. So now what I'm going to do is I'm going to swap. I'm going to view this probability as an expectation and just swap these expectations. And what I end up with is the probability that a random vector W gets mapped to 0. And the point is that if H has lots of large singular values, it kind of wants to push a random vector W in all sorts of different directions. So if H has lots of large singular values, this should be more anti-concentrated. And it turns out this heuristic is true, and we can show that this is at most epsilon to the d minus k. So d minus k corresponding to the number of large singular values. So it's pushing d minus k directions and making them large. So that's how we kind of invert the randomness and treat this as look at the probability that for a fixed H, a fixed pseudo-random H, what's the probability that a random W gets mapped to 0? So here you can see numerically, at least in the numerology, this trade-off. This K is helping this probability, but hurting this probability. And it turns out that, well, we can just see that the K equals 0 term is dominant. And so we get an epsilon to the D times epsilon to the N minus D for a final bound on this expectation of epsilon to the N. And so then Markov's inequality gives us a bound of L to the minus 2N, which actually isn't quite enough. If you remember, I had an L to the minus 2N there, but the fix there is just to do a look at the second moment. Okay, and so that adds a few extra complications. Okay, so in the last couple of minutes, let me just talk about how do we control this probability, the probability that HU equals 0 and EK is random. Actually, since I have not much time, let me skip a slide.
You have 2 minutes.
Yeah, okay.
And 5 minutes for questions and answers.
Okay, great. Oh yeah, I probably have time. So let me just first be less ambitious. Rather than trying to control these two events simultaneously, let me just think about this event. So here's a fixed U. What's the probability that HU equals 0 with a random H? So for this, just think about one row of H and think about what HU is. So I get, if I call one row of H tau, the first entry is going to be the inner product of tau and U. And so this probability is actually just going to be the probability that tau U equals 0 to the power of the number of rows of H. So here I'm using that H is IID, which is nice, kind of gives you a way of making this a one-dimensional problem. There's one advantage of working with H. There were n minus d rows of H. So then we're led to the question, well, given a U, how large is this probability? And this kind of question is known as the Littlewood-Offord problem. It's pioneered by Littlewood-Offord in a different context, studying random polynomials. And it's been incredibly useful to study the inverse problem, which says, if this is large, what can we say about the structure of U? Because we also want to do some counting. If you think about the union bound, we might want to know, well, how many U is this large for? And there's a kind of meta theorem out there that says that if this is large, then U has some additive structure. And the additive structure useful for us is the following. I'll define the least common denominator of U as the smallest dilate, the smallest theta, for which theta times U is close to the integer lattice. So vaguely, this is saying that U is well approximated by a rational vector with small denominator. If the LCD is small, then I'm well approximated by a rational vector with small LCD. So this is some nice additive structure. And that's the notion we're going to work with. And so a big step towards bounding this probability that I mentioned before is this new inverse Littlewood-Offord result that lets you say the following. If the probability, well, so suppose W is a matrix with orthonormal rows, and tau is like a row of my matrix H. So 1/4 lazy here means it's 0 with probability 3/4, plus minus 1 with probability 1/8. If not only this probability is large, but this probability and some funny extra conditions. So this is like a random walk with a bunch of kind of soft constraints added to it. If this is large, then my least common denominator is small. So that's the additive structure. And it turns out that this condition is extremely harsh condition. So this is satisfied is very rarely satisfied by U. So this is a inverse Littlewood-Offord type result where you can think of this constraint as corresponding to this, corresponding to the condition HU equals 0, and this weird condition coming from this matrix W encoding the small eigenvectors of H. And it's nice to note that at k equals 0, meaning just delete these conditions, we recover a classical inverse Littlewood-Offord result of Rudolphson inversion in. Okay, let me end with a nice picture of Littlewood and Offord. There's actually a few London people in the crowd. So Offord actually has Cyril Offord has some cool connections. He actually did his undergrad at UCL, then went to Cambridge, then came back to London, then went back to Cambridge, and then finally ended up at the LSE as a chair of mathematics, where he was very hugely influential on mathematics at the LSE. Okay, I'll end there. Sorry for running over. Thank you for listening.
Thank you, Matt. Okay, let's first thank Matt. We have a few minutes for questions.
What kind of constant would you get out of this proof?
Yeah, good question. We tried and we got something like 2 to the minus 2 to the 50 or something.
Okay.
So something relatively small, not quite far away from 1/2.
Okay.
Yeah.
Sorry, you have started the proof by the turn from A to M. How it was done? Can you comment?
You mean this replacement step? Yeah.
Equality between probability for A and for M. How it has appeared?
Yeah. Let me just go back to the very beginning.
In the beginning.
Yeah.
You know,
yeah. So yeah, I kind of I make this comparison here. This is just by comparing like Fourier transforms. And it turns out that the Fourier transform of this event is pointwise bounded by the Fourier transform of this event. So it's just a simple Fourier calculation. But the intuition is that M is like much lazier. It's got lots of 0 entries, so it kind of wants to map things to 0 more than A does. But to make that rigorous,
matrix element of H are plus and minus. Oh yes, I see.
Yeah, H is plus or minus or 0. Yeah.
Thank you.
I actually have another quick question, or maybe not too quick, I don't know. So what is the intuition why the problem for symmetric matrices is harder, or significantly harder than the matrices without this constraint? And also, why the uniform case is harder than the non-uniform case, if you can comment on this.
Yeah, so for the first one, it's basically, I mean, one reason is suppose we had this matrix B, where B is totally IID. Well, what's the probability, let's again say like a row is, let's just call a row of B tau. This is the probability that V tau is 0 to the power of n. Sorry, I'm not sure you can see that. So
Yeah,
immediately you kind of get this nice, you essentially have a one-dimensional treatment of the problem, whereas no such thing is available in a symmetric case. I mean, you could also make, it's kind of philosophically interesting, because you could also say, well, a matrix is symmetric, so the eigenvalues are real, so maybe they're easier to understand. But it turns out that this perspective, no one has made that useful. So yeah, the reason why old methods have failed, well, at least methods to attack this have failed for the symmetric cases, you don't have this kind of one-dimensional perspective.
But for non-symmetric matrix, the answer is unknown, yes? For non-symmetric case.
So for non-symmetric, meaning just everything IID, then much more is known. Then we have this result of Tikhomarov at the very Tikhomarov getting the correct bound of 1/2 to the n. So non-symmetric here, I'm interpreting as just like everything IID.
Okay. Mm-hmm.
So this is much easier. Yeah.
Mm-hmm. Mm-hmm.
And if we have still 1 minute, so what about this Jane Sine-Sony result?
Yeah, it's a really good question. I actually I don't understand. Well, I haven't looked at this paper carefully enough to understand why the non-uniformity really helps here.
And could it possibly help in your case? Also.
Yeah, that's a good question. So if we were non-uniform, could you refine this probability? I don't know. Yeah, that's a really good question.
Okay, cool. Thanks a lot.
But yeah, I should say we can deal with much more general distributions than this. We just need a kind of something like the entries are sub-Gaussian, but we still just get an exponential bound, nothing fancy like 1/2. And then you can ask about, okay, so sorry, when you go to sub-Gaussian, you're talking about continuous distributions, so you're almost certainly going to be non-singular. So then you start asking about the least singular value, like what's the size of the least singular value? Yeah.
So Matthew, you also. Oops.
Sorry.
Okay.
I think.
Sorry, it was open twice accidentally. So regarding Andrew, you don't hear me.
Yeah,
we hear you. We hear you.
Yeah. Sorry.
We hear you.
Okay, maybe Gal can ask later, Matt, the question, but we need to move. So
yes,
thanks a lot, Matthew.